Hi, everyone. Today I'm gonna talk about a toy project that we recently developed called eqsat. It's an equality saturation dialect for non-destructive rewriting. It's basically combining MLIR and EGRAPHS because both are cool. So here is the simple compilation flow that takes a source code and compile all the way to the executable binary. So here we can see the code is transformed into or lowered into different IRs, increasingly lower level of abstractions. So we might have a loop level or then instruction level. So X useful. So we can use that to rewrite our expressions. So apply this rewrites non-destructively. So user can define new rewrite rules for different patterns based on their application domains, and then they use E classes to analyze the properties of these expressions. So it's quite easy to support rewrites at a different level of abstractions. But the problem is most tools build on top of X, and they are not tightly integrated in the compilers. So the developers often have to implement these conversions between EG and their frameworks. So for example, like from eGraph to their program representation. And in most time, it will require a lot of development efforts to do the translation. And most importantly, the equality information of the program is often lost during the conversion. So it's not possible to carry all the equality information across the abstractions in this compiler, transformations like function calls or function inlining analysis between different abstractions is quite challenging. Yeah. So CraneLift has done a great job. So it's a JIT compiler backend, most used for compiling WebAssembly and the Rust code. So it embedded like eGraph into their IR, also called as acyclic eGraphs. So they have optimizations like global value numbering and looping invariant code motions are handled by the eGraph optimizations. So there's no real conversion. So everything is done natively. But a limitation is that it only works in CraneLift. So it's not possible to extend a higher level of the abstractions earlier in the compilation. So for example, if I wanted to target a deep learning application, then I cannot really do some tensor level primitives. So the motivation is, how about we combine the best of both worlds? So can we actually implement a tightly integrates MLIR framework that with eGraphs? So maintain equality relation throughout different abstractions with different compiler passes. And ideally, we should be able to handle equality saturation at different level. So what is MLIR? So MLIR is one of the most popular framework in compilers. So has many different dialects at different level of abstractions. Here we have three set of different examples. So the first one is lineage. It has high-level linear algebra operations like matrix multiplications. So it operates on the tensor level of values. And there are also lower level of abstractions like structured control flow for. So that's basically represent a for loop. And we also have other operations like arithmetic operations for addition and multiplication, and also memory operations like load and store. Even further, we can lower this into specific targets. So it's like LLVM floating point add or RISC-V floating point add. So the idea is like, or our vision is try to build equality saturation on top of MLIR to give our extensible flexibility to explore across all these dialects. So the question is, how do we represent eGraph in MLIR? Like the key idea is like we don't want to translate MLIR code to EG, and this is what have been done. So can we actually express eGraph in MLIR in this case? Here is a simple example. On the left, so we have a function that takes one argument and return one result. So the right-hand side is basically the AST of the program. We have a times a constant of 2. So intuitively, this is the eGraph that we have. I guess everybody is bored with the figure on the right. So the interesting thing is, how do we express this as MLIR code on the left? So so basically we introduce eClass op as an operation that takes a variable number of inputs and return a single output. So in this case, all the values are passed to an eClass operation and then return a result. So what we observe is each arithmetic or each non-eClass operation will take a set of operands in eClass and then return an enode. And the enode will be passed to eClass, right? So how do we express different enodes in the same eClass? So one possible example in this case is a shift left by 1 is equivalent to a times 2. In this case, we will, so the black lines of code represents the new expression. So first we have the new constant that is 1, and we wrap them as eClass, so that's straightforward. And then the shift operation is equivalent to the multiplication. So what we do is we introduce a new operator and we insert the value into the operand list of this eClass. So we will have, so basically we just introduce a new representation. We have all the problem that egg has experienced before. Here we focused on the expression of this different eGraph representations in MLIR. So one well-known thing is cycle. And in traditional MLIR program, or in most sequential program, we cannot represent cycles because variables has to be used when after it is declared. MLIR has a structure called graph regions that allows programs to be, or graph to be represented in MLIR. So in this case, we use graph regions to represent eGraphs. So it's more like standard SSA CFG regions. So this allows us to express regions in IR. Oh, sorry, cycles in IR. So how about union or rebuilding? So we consider that as a compiler transformation. So the insight is, can we actually reuse existing compiler optimizations to help our rebuilding process? So egg introduces has union, which is like efficiently maintain the congruency invariance. So here we have an example, like we have two. After we apply rewrite rule, we come up with different expression of eGraph. Now we want to merge them together. So if we find that A and B are equivalent, so then we can easily see that res0 and res1, which is function of A and B, are equivalent. But currently the graph on the left is not really an eGraph because these two eClass should be merged together. So what happens here is we can run this CSE pass to remove redundant terms and then keep only one eClass in the graph. Right. So the other thing is, how about rewrite rules? So traditionally in egg, we have rewrite rules declared as a pattern rewrite. And in MLIR, we also have pattern-based pattern rewrites. So user can basically specify a pattern, input pattern of the MLIR operations, and they specify how this can be translated. So our implementation is based on PDL Dialect, which is called Pattern Definition Language. So it's basically the code might look quite complicated, but the key idea here is the user can specify the patterns of MLIR operations, and they can also specify how the transformed MLIR code look like. So this is equivalent to the rewrite rules. So what I can share here is a very simple example. So it's like if we have multiplication, that's x times y, and we can find an equivalent term that is y times x is equivalent to y times x. The first thing that it does is the PDL rewriter will try to identify these operations using Python-based rewrite, and then we will find the results by identify the E-class of this operation, and then we will basically find this E-class will contain multiple E nodes. So there are two more operations that implement in PDL rewrite, but basically what it does is it will insert the newly created term and insert that into the E-class. So everything sounds very straightforward, but it's not. So if you actually apply PDL rewrites directly on to MLIR programs, then we find something interesting. So ideally, with rewrite rules, we have different levels. You can add in different equivalent terms into the eGraph. That sounds really fancy. But what we find here is we might actually got a different isolated eGraph because they are targeting different abstractions. So that's not what we want because, for example, we have for loop, then we have eGraph for the for loop header or the structure, and we also have another eGraph for the loop body. But actually, there are correlations between the eGraph, the loop and its loop body. So this is something we haven't solved yet. We are currently looking into this problem. So the main reason is because PDL does not handle regions. So what we are looking at is create correlations between these two levels and then create a region-friendly eGraph representation. Yeah. And there are also other interesting open questions. So how do we handle operations with results? So if we look at most egg examples, we expect the expression will return a valid value, but operations like store does not return any value. So we could, like in traditional MLIR, we could represent this as a non-value, but then we realize different non-values might represent different things, so they are not equivalent. So the other thing is evaluation. So once this framework is working, what's the best, or which compiler passes will benefit the most? Like there are many compiler passes available to be integrated into the eGraph, but which one will be super interesting? So particularly we have an example in a paper is taking functional inlining as an example. But it would be nice to explore them intensively across different passes. The other thing is application. So it's like how this framework can benefit different applications by unifying the compilation and eGraph into the same framework. So we are looking at Herbie-like floating point optimizations and also like applications that require multi-level end-to-end compilation. Yeah. That's everything. Cool.
Thanks for the great talk. Yeah, okay, great. We have lots of questions.
Thanks for the great talk. And one of the most important thing that a compiler must do when you use eGraph is to extract the best fitting instructions from the representation that you just described. So I think that is not clearly mentioned here. Can you clarify how would you implement an extraction?
Right. So extraction is a big problem for eGraph. I agree. So currently, I think we are still. So this project is still at a very early stage. We are focusing on how do we represent eGraph in this IR. Currently the extraction is quite naive, just iteratively going through all the E nodes and find the best one and extract. We haven't explored all the algorithms, but I guess the problem is the same for EGG, or other eGraph tools. So we can, if we have an algorithm, we can easily migrate to the MLIR framework.
So super cool talk. Thank you for giving this. And as the person who put eGraphs into CraneLift, also very cool to see it, being integrated into IR in different ways. One thing that wasn't completely clear to me about your mechanism, you mentioned that CSE is used to do the E-class merging. So I can see how that works if you have two different definitions of the E-class that are exactly the same, right? But if you have like overlapping but not equivalent E-classes, so you have one E-class of A and B and another of A and C or something like that, which can happen if you like just merge in one of those values. Do you need CSE to be aware somehow of the semantics of E-classes?
So that's a good question. So I think at the moment we haven't observed this happening, and the main reason is because when we do rewrite explorations, I think it's currently sequential. So the E-nodes are observed like incrementally, so we haven't observed that. So the key idea, probably like when we find this happening, then we will think about how to handle that. But our current implementation does not have this problem. Yeah. Thanks.
Thank you. I have a couple of questions that I actually catch you after, but maybe the big question I kind of struggle to grasp is like, what's the main advantage you get of representing the eGraph as an IR, rather than just implementing this in C++ right next to, like in the MLIR framework, and you just do kind of X style, but you're not representing it. So what do you get by actually embedding the eGraph into the IR?
Right, that's also a good question. So the initial motivation of the project is like, it's cool, we should do it. And we haven't thought about this. Now we're thinking about this as well. I think the key benefit is like removing translation overhead. And in eGraph, so one thing that we think is quite interesting, but we haven't explored yet, is like in the eGraph, can we actually like using existing compiler analysis, so we can guide the search without translation and keep the equality information across, like maintain the equality information all the way rather than come back and forth. You can, you can implement eGraph in Rust natively, that's no problem. That's another way of thinking about it, like implement all the compiler optimizations in Rust. But I think we haven't explored this yet, actually, yeah. So we don't know.
I think maybe a refinement of that question, which is something I had. It's like, what are you gaining by putting these eGraph operations in the IR versus like inside of MLIR, like next to the data flow framework they have, you add an eGraph framework, and then you can pull operations in there. Like, is this purely help out the implementation, or is like, what are you gaining by doing this?
Right. Yeah, it's a similar question. So I think these are the questions that we are exploring. So we don't know yet, because we haven't played with any other dialects as a case study or benchmarks yet. So the key, I think, what I have to thought about is like, there are different regions, there are different rewrites that's existing. It's mostly developing efforts. So it's like, it will take a lot of effort to use AG, but if this works, then you can probably just connect with any MLIR framework or existing framework that helps, right?
Okay, let's thank the speaker one more time.
Thanks.